In the previous lectures, we've already discussed cutting planes for pure integer linear sets and for mixed integer linear sets. In this lecture, we're going to discuss cutting planes for mixed 0-1 linear sets. Of course, this is a special case of mixed integer linear sets, but it turns out that it's much simpler and that we need much less in order to obtain finite convergence, and also we can obtain a very nice bound on the number of closures that we need to obtain the mixed integer hull. We consider mixed 0-1 linear sets of this type P, where P is a polyhedron as usual, intersected with binary points for the x variables and just r to the p for the p continuous variables y. Without loss of generality, we can consider a polyhedron P with x variables that satisfy xi between 0 and 1 for every I. As always, our polyhedron is given by a system of linear inequalities. We can now define what is a lift and project inequality. This is simply a very special case of a split inequality. It is a split inequality relative to a split of a very special form, xj between 0 and 1 for some j between 1 and n. So essentially, we're taking only the splits that are axis aligned. Directly from the definition of split inequality, we have that a lift and project inequality can be equivalently defined as an inequality valid for the convex hull of the points in P that satisfy xj less than or equal to 0, union the set of points in P that satisfy xj greater than or equal to 1. This set will be very important in our subsequent discussion, and so we're gonna call it Pj. We have an example here on the left. We have our polyhedron P, which is the largest polyhedron in this picture, and then we have a variable xj here on the horizontal axis. We see that the polyhedron indeed satisfies xj between 0 and 1, and now we take the set of points in P that satisfy xj less than or equal to 0, which is this segment over here, the set of points in P that satisfy xj equal to 1, and we take the convex hull and we obtain this quadrilateral Pj. This example also makes us understand something crucial about this set Pj. In fact, all the points in P that satisfy xj less than or equal to 0 in fact must satisfy xj equal to 0, and similarly all the points in P that satisfy xj greater than or equal to 1 must satisfy xj equal to 1. So we have substituted here the inequalities with the two equalities, and we can write then Pj equivalently as the convex hull of the points in P with xj either 0 or 1. In particular, Pj is the convex hull of two faces of P. This fact allows us to describe the set Pj in a very nice form that will be crucial in the proof that we will see later. So, Pj, we just defined it as the convex hull of the points in P with xj either 0 or 1, and now, for simplicity, let's think about the case where P is a polytope, so it can be written as the convex hull of its vertices. Then Pj can be equivalently written as essentially the same set, but where we replace P with the set of vertices V. To see this equivalency, one just needs to observe that every vector in a face of P can be written as a convex combination of its vertices. Of course, this observation is only valid for polytopes, but a similar property holds if P is unbounded. It is a very good exercise to think about the unbounded case and try to formalize this property in this more general setting. As we've already seen a couple of times in this chapter, first for splits and then for lattice-free polyhedra, we can write Pj as the projection of a higher dimensional polyhedron defined with the Balázs extended formulation. In this case, Balázs extended formulation takes this form. There's nothing new. And historically, the name lift and project given to this inequality exactly follows from the fact that Pj can be obtained by first lifting into this higher dimensional space, where we write the extended formulation, and then by projecting it down to the original space of the x and y variables. Now we can define the lift and project closure of the polyhedron P, And it is obtained simply by intersecting all the polyhedra Pj for every j between 1 and n. We're going to denote the lift and project closure with this notation Lp of a polyhedron P. We have an example here to discuss, so that's our polyhedron, and we just have two variables. They're both discrete variables, so x1 and x2, and the polyhedron, as it should, is contained in the unit hypercube. Now, the first thing we should look at is P1. So what is P1? By definition, it is the convex hull of the points in P that satisfy x1 equal to 0, which is just this point over here, and x1 equal to 1. So that's why we obtain this segment. On the other hand, the set P2 is defined as the convex hull of the points in P that satisfy x2 equal to 0 or x2 equal to 1. So we obtain this segment. Therefore, the lift and project closure is the intersection of these two blue segments, and so it's just this point 1/2, 1/2. As you can see in this example, the lift and project closure is not always equal to the mixed integer hull of our polyhedron. Therefore, as usual, we want to apply the lift and project closure recursively. So the first thing we need to do, as always, is to show that the closure is indeed a polyhedron. But in this case, it's much simpler than in the previous cases that we have seen. In fact, every Pj is a polyhedron by Balázs extended formulation, and we're intersecting only n such polyhedra, and therefore the intersection must be immediately polyhedral. One more thing to observe is that the split closure is always contained in the lift and project closure. This is because every lift and project inequality we have seen is also a split inequality. Now that we know that the lift and project closure is polyhedral, we can define the lift and project closure number t as we did in all other previous cases. And we can similarly define the lift and project rank. When we talked about split inequalities, we saw in example 5.11 that the split rank might not be finite. However, in the special case of mixed 0-1 linear sets that we're discussing now, we will see that on the other hand, the lift and project rank is always finite. Since the split closure is always contained in the lift and project closure, this also implies that the split rank is always finite for the special case of mixed 0-1 linear sets. All these results will actually follow from a much stronger result that we now show. In order to state it, we need to define one more polyhedron. So recall the definition of Pj, we've already seen it before. This is the convex hull of the points in P with xj either 0 or 1. Next, we define our new object P superscript t. This set is obtained from P as follows. First, we convexify P with respect to the index 1. Next, in what we obtain, we convexify again, but now with respect to the index 2, and so on and so forth recursively until we convexify with respect to the index t. Now it's clear that P superscript t always contains the lift and project closure number t of the polyhedron P. And to see this, one just needs to observe that at every iteration in the set P superscript t, one convexifies only with respect to one index, while at every iteration of the lift and project closure, one convexifies with respect to all indices separately and then takes the intersection of them. Let's see an example of this set P superscript t, and we're going to visualize it once again in our old example here. So for this example, what is a P superscript 1? This is very simple because it's just our old set P1. Therefore, it's the convex hull of the points in P that satisfies x1 equal to 0 or x1 equal to 1. So here it is. That's our set P superscript 1, which coincides with the old P1. But now, what is a P superscript 2? Now we have to take this polyhedron, P superscript 1, as the starting point and look at its points that satisfy x2 equal to 0 and x2 equal to 1 and convexify. But there's no point in P superscript 1 here or here, therefore P superscript 2 is the empty set. We are now ready to prove the main result on lift and project. It's called sequential convexification. We have a polyhedron P with x variables contained in the hypercube 0, 1 to the n and with other p, y variables. Then, for any t between 1 and n, we have that the set P superscript t is the convex hull of all the points in P that have the first t x variables binary. In particular, if you look at this expression for t equal to n, we have that the set Pn is the convex hull of all the points in P that have x variables binary. Now let's prove the sequential convexification theorem. I will only give a proof in the case where P is a polytope. Let me write this. This is a proof. For the case where P is a polytope. Denote by capital V the set of its vertices. In this proof, we're going to use several times the fundamental facial property of our polyhedron that we discussed in the slides. Let me write it down. We use several times the following fact. Each vector in a face f of P can be written as a convex combination of the vertices of P in F. And essentially, the reason why I give this proof only for the case where P is a polytope is exactly because of this fact. This fact is only stated for polytopes, and as I told you in the slides, you can extend this to a general polyhedron, and this is exactly what you need in order to obtain a general proof that works for any polyhedron. We're going to prove this theorem recursively, so let's look first at P superscript 1. P superscript 1 is just P1, and this is by definition the convex hull of all the points in P with x1 in 0, 1. And our fact immediately implies that this is the convex hull of all the vectors in V with x1 in 0, 1. And this is exactly because the set of points in P with x1 in 0, 1 is exactly the union of two faces of P. So now let's apply recursively this argument. Recursively, we obtain for t equal to n pt is, what is this? By definition, it is, well, p1, 2, and so on and so forth, t minus 1 until t. And so this is p superscript t minus 1 subscript t. So now let's use the definition of our subscript t. So this is the convex hull of all the points in P superscript t minus 1 such that xt is in 0, 1. So again, we can use our factor for the same reason as before, as this is the convex hull of all the vectors x in vt minus 1. So what is vt minus 1? Well, I should have defined above this set here as v1. And so recursively we know who vt minus 1 is. So getting back to our equality, this is the convex hull of the points in vt minus 1 with xt in 0, 1. And at this point, let's call again this set of points vt, and let's understand exactly who this guy is. Note that vt is, what is it? So let's look. Our definition of vt tells me that it is the set of points in vt minus 1 with xt binary. But if we then look back at who vt minus 1 is, this is the set of points in vt minus 2 with also xt minus 1 in 0, 1, and so on and so forth until we get to v1. And so we will obtain that vt is the set of points in V with all the xi's in 0, 1 for I that goes from 1 to t. Let's write it down. Great. So at this point, we just need to apply our factor one last time. Therefore, conv vt. So conv vt is exactly our set p superscript t that we want to characterize as in the statement of the theorem. So what is conv of the vt? Is, let's replace our vt that we just obtained. So this is the conv of all the vectors in V with x1 until xt in 0, 1. Now we can apply again our fact, but in a little bit of a different way, because now for every possible x1, xt in 0, 1, this is again a face of our polyhedron P. And so I can apply again the fact, and instead the only difference with the above two ways we apply the fact is that now we don't have only two faces, but we have essentially 2 to the t. So this is conv of the set of points in P with x1 until xt in 0, 1. And this is exactly what we had to show. So this concludes the proof of the convexification theorem. Let's get back to the slides. The sequential convexification theorem in particular implies that the lift and project rank of P is at most equal to n, which is the number of binary variables. Furthermore, since the split closure of P is contained in the lift and project closure of P, we also have that the split rank in this case is bounded by n. We should note that in this theorem, it's of course fundamental that the x variables are indeed binary. In fact, even if we have variables x in 0, 1, 2, then the theorem is no longer true. An example that shows that sequential convexification no longer holds for 0, 1, 2 variables is the example that showed that split inequalities don't converge finitely to the mixed integer hull. In that case, if you remember, we had two discrete variables, x1 and x2, and one continuous variable y, and the discrete variables were between 0 and 2. One might wonder if the upper bound n on the split rank for mixed 0, 1 linear programs is tight, and in fact, it is. This can be seen by giving examples of polyhedra P for which the split rank is exactly n. And a very simple example is this polyhedron written here. So in this polyhedron, we look at any subset capital J of 1 to n, and then we write the inequality sum of all the xj for j in j, plus 1 minus xj for every j not in j greater than or equal to 1/2. This polytope is also known in the literature as cross polytope, and we have here the cross polytope in dimension 2. In this case, it's defined exactly by 4 inequalities because that's exactly the number of subsets of 1 and 2. In this example, we have only x variables, and so the mixed integer HA of P is exactly P intersected 0, 1 to the n, and you can easily see that this is the empty set. What you can show is that the split closure number n-1 of P is different from the empty set, which implies that the split rank of this polytope is exactly n. So let's stop for a second to recap what do we know about the split rank. Well, we saw that in the general case, when integer variables are not binary, then no bound may exist at all on the split rank. On the other hand, if all the integer variables are just 0, 1 valued, then not only the rank is always bounded, but is also bounded by just a number of variables. Therefore, it's clear that split inequalities are much more powerful whenever we only have binary variables. And this brings us immediately to the idea of transforming in our formulation every integer variable into the sum of binary variables. And there are several ways to do so. In this way, while our original problem doesn't have a finite split rank, the new one always have a bounded split rank, and this bound will coincide with the number of variables in this new formulation. Now the question is, how should we replace an integer variables with a bunch of binary variables? Well, there are several ways of doing so. The most immediate idea is to just use a binary expansion of an integer point x. Namely, we write x as the sum of 2 to the I zi for binary variable zi. In this case, if our original integer variable is between 0 and u, then we need log u new binary variables. But this is not the only way to do so. A second way is to write our integer variable as the sum of the I times zi, where I ranges from 1 to u. In this case, we only want one of the zi binary variables to be equal to 1, and so we had the constraint sum of the zi at most 1 and zi binary. If we look at the number of variables here in this second example, we're definitely using more variables because we now have exactly u variables, while in the previous case we had log u. Finally, let's see a third way of formulating an integer variable x with binary variable zi. In this case, we have that x is the sum of all the zi for I equal 1 to u, and in this case you see the difference with the previous is that we don't have I, and in this case, for example, if you want to obtain x equal to u, you must have all the zi variables at 1. Using this equality, there are several different ways of obtaining any integer x between 0 and u as the sum of zi's that are binary. So in order to break symmetry, you can, for example, add inequalities of the form zi minus 1 greater than or equal to zi for every I. In any case, these are just three possible ways that allow you to delete integer variables from your formulation and replace them with binary variables. At this point, the new formulation we know will have a bounded split rank. However, from a practical perspective, it's unclear at this point if we can gain any practical benefit from making such a transformation. At this point, we simply don't know enough to argue if, in general, this is a good idea or not. And this concludes our video on Lift and Project.